Our series of lectures on elementary quantum mechanics. Today, in part 3 of my discussion on hydrogen atom, I will try to talk to you about the shapes of orbitals. We will learn about what are the shapes of different orbitals and why they are as they are. The session is planned as follows. That is, to begin with, we will try to briefly review what we did in the previous sessions, that is part 1 and part 2. Thereafter, what are the hydrogen-like wave functions. Thereafter, we come down to the main theme of today's session, that is the shapes of orbitals. And in this context, we will begin with understanding what are the radial wave functions, how do they look like, what is their significance and things like that. And then thereafter, we will pick up the angular part of it, the angular wave functions. And towards the end, we will try to sum up what we do today. Let's move further and recall what we have done in previous two sessions. You would recall that we basically started by defining what is the problem of hydrogen-like ions, and then thereafter we formulated a Schrodinger wave equation for the same. Thereafter, we discussed the strategies, because what happened was, if you remember, that the Schrodinger wave equation happened to be quite complicated one, and it could not be solved in the Cartesian coordinate system. So, we discussed how to get over them, and in the process we went from kind of Cartesian coordinate system to polar coordinates, and then thereafter we used separation of variables and things like that. So, we discussed all those strategies. Thereafter, in this, as a consequence of that, we were able to separate the equations into three parts: the r part, theta part and the phi part. And thereafter, we did not get into the process of solving these equations. Instead, we stated the results and discussed the significance of that. We will come to that a little while again later on. And towards the end, in the last session, we explained the significance of quantum numbers which are obtained as a consequence of solving these equations, because all these equations, when they were solved, they gave us the quantum numbers that we have talked in the previous session. Okay. Now, continuing with this recall, because I want to put things in perspective, you would just recall that when we had Schrodinger wave equation for hydrogen-like ions in polar coordinate system, the equation looked something like this. The important thing here is that we have got psi, that is a wave function. The total wave function for this happens to be a function of r, theta and phi, the three polar coordinates, and then this del square happened to be the Laplacian operator. That is fine. Now, the strategy we have evolved was, that is, in order to solve this equation, we had to make an assumption, and the assumption happened to be that this overall wave function psi, the function of r, theta, phi, could be assumed to be made up of three parts. One called as a r part, that r wave function, which depended on r, then a theta depended on theta, and phi depending on phi. The capitals are the wave functions, and the smaller caps here are the corresponding variables in that. Thereafter, we did see how to separate the equations, and then these separated equations were called as the r equation, theta equation and phi equation, and thereafter these equations are supposed to be solved in the order of phi, theta and r, that is a reverse order, just for sake of mathematical convenience. And when we solved these equations, we came across the wave functions, the corresponding wave functions. Each wave equation when solved, each part of the wave equation when solved gave set of wave functions. When we solved phi equation, we got wave functions called as phi m, because the m was the magnetic quantum number. That means these wave functions depend on m. So, there are a set of wave functions we got there. Similarly, when we solved theta equation, we got another set of wave functions called as the theta wave functions. Thereafter, when we talked about the r part of it, similarly r part also gave us a number of wave functions. So, what is important here is that this r will depend on the quantum number n and l, and so on and so forth. Okay. So, if we have got all these wave functions, because today we want to see what do these wave functions mean to us. If we go further, just before we come to the meaning of these wave functions, what typically is done is, if you look at that there are three components of the equation, r equation, theta equation and phi equation. Out of these three components, two parts, that is the theta part and phi part, basically they generally are combined together to give us what is called as a angular part of the wave function or wave function. That means the wave function happens to be r into theta into phi. So, this theta phi is called as the angular part, sometimes given as y L m L. L is the azimuthal quantum number, m L happens to be the corresponding magnetic quantum number. And in that context, we can represent our wave function, which depends on r, theta and phi, to be made up of two parts. One is the radial part, that is the r part of it, and then this y L m, it is called as the angular part. So, that is what I wanted to bring home, that is our wave function can be seen as made up of two parts, the radial part and angular part. And now on, we will try to see what does the radial part convey to us, what does the angular part convey to us, and then how do we put the two together to get the shape of the orbitals as we know of. Okay, let us have a look at some of the wave functions of the common atomic orbitals. So, this is my wave function for 1s orbital, this is for 2s and so on and so forth. So, that basically I have given the corresponding contour numbers, and the respective wave function over there. So, what you see is, if we look at 1s part, we just see that it has only r here, even 2s has got r. If you look at the p orbitals, I find that there are some thetas are there, phi's are there, here theta is there, theta and phi are there. So, this has a bearing on it, because these basically have some kind of an angular dependence, whereas s orbitals have only the radial dependence. We will talk more about this as we proceed. Let us have a look at some of the radial distribution curves. Basically, what we do is, we take the radial part of the wave function and make plots of the wave function as a function of r. They are called as a radial distribution curves. Let us look at some of these curves here. This is very important. Now, what I am showing here is, so this is radial distribution curve for 1s orbital, this is for 2s orbital, this is for 3s orbital. Let us try to understand it, let us try to have a look at it. What you see is, for a 1s orbital, what you find that to begin with, this is my distance r. So, at 0 there is a nucleus, we have a nucleus. As you are moving away from the nucleus, what is happening, that we are trying to see. We find is that very close to a nucleus, this value, that r, the wave function has got a very large value, and as I move away from the nucleus, the value is decreasing very sharply, exponentially, and very soon comes down to close to 0 and continues thereafter. That is what happens in case of 1s orbital. If I look at the same for 2s orbital, what I find is that again the value is very large, close to a nucleus, it comes down sharply as before, but after certain distance from the nucleus, this value starts becoming negative, because this becomes 0 here, then becomes negative, comes to a certain minimum, starts increasing again, and after certain distance here, it comes to 0 and then continues thereafter. And if I look at that of the 3s orbital, it is again very interesting. Large value to begin with, comes down very sharply, becomes 0, starts becoming negative, comes to a minimum, starts increasing, comes to 0 again, starts becoming positive again. Then thereafter comes to a smaller maxima here, and then starts decreasing and comes down to, tapers off, comes parallel to the x-axis. So, what you see is that what I am trying to look at is, I am looking at the radial distribution curves for 1s, 2s and 3s orbitals. What I find is that we know that psi, the wave function per se, does not have any physical significance, that we have discussed earlier too. But what I am finding is that the wave functions, the plot of wave function as a function of the distance from the nucleus happens to be different for the 3 orbitals I am talking about. We will read more into it as we proceed. Now, we have also learnt that the square of the wave function, that happens to be the measure of probability. I made a statement earlier, it is not probability, it is called as probability density. Let us see, if I take the square of wave function, how does it now look like? So, basically I am trying to make plots of the probability density, that is the wave function square, as a function of the distance r. If I look at these 3 curves again, this is for 1s orbital, this is for 2s orbital, this is for 3s orbital. Now, if I see it here, this is similar to what we had in case of the wave function. The number was very large, came down very sharply, but now what I am seeing is that this is still very large because it is a square, it becomes much larger. But when it decreases much more steeply as compared to the wave function only. But all said and done, it is very large here and comes down to 0 and then continues thereafter. But if I look at the 2s part of it, in case of 2s, the r square value is very large close to the nucleus, comes down sharply, comes to 0 and then thereafter it becomes small positive value here. It comes to smaller maxima. So, we have a positive thing here, and this positive is coming because in the wave function part we had a negative component here. With the negative component, if I take a square of it, it becomes positive. That is how I am getting a small maxima here. If I look at the 3s one, again large value comes down to 0, then there is a smaller maxima and then it comes to 0 again, continues, and then again another maxima is there. So, there are two maximas here and one large number here. So, that is the kind of curves I get here. So, they are the probability densities. How does the density of electron vary as a function of distance from the nucleus? Now, let us try to understand that I am talking about probability density, but does it mean probability? The answer is no. It is not same as probability. Let us try to understand the difference between the two things. We know that mass is density into volume. Similarly, the probability is the probability density into the volume element here. Let us try to understand it here. Now, this curve what we are showing here is it's a schematic presentation here. So, there are three things in this. Let us try to understand each one of them. Now, this we have just seen that if I take the square of wave function, make it a plot of it as a function of r, I find it decreases very sharply. That is fine. Now, I want you to now have a look at what does the volume element mean here. Let us understand this. Now, we know that there is a small tiny nucleus in the center of the atom, and then as you are moving away, the electron is distributed around that. Now, if I look at the nucleus in the center and think of a small sheath, okay, let the nucleus have certain kind of radius, it has certain volume there. Now, think of a small sphere around the nucleus. Now, the volume of this small sphere will be very, very small, because if I look at my nucleus has a distance radius of r, and this happens to be dr. So, r plus dr, if I take the 4 by 3 pi r plus dr cube and then subtract from this the volume of the nucleus, I get the volume of this small sheath here. Now, think of yet another layer again, think of many layers. If I do that, I find that each successive layer has a larger volume. You can see it. Now look at, suppose I take an onion and peel it off. If I remove one peel, so the outermost layer if I remove, if I look at the volume of that, is much larger. If I take the inner layer and so on and so forth, I mean it is just a reverse of it here. The probability happens to be the product of these two. Okay. So, what happens is, to begin with, the probability density is very large, but the volume is very small. So, as a consequence, the probability happens to be very tiny, very close to 0 here. As I move away from the nucleus, this component is decreasing sharply, whereas the volume element is increasing very sharply. The resultant of the two is such that the probability starts increasing, and at a certain distance it comes to maximum, and then thereafter this factor overtakes this factor and the probability starts decreasing, and that is how it varies there. So, this is going to be my typical probability curve of finding the electron as a function of distance from the nucleus. Now, that is what I am looking for. Okay. Let us look at the radial probability curves. I am showing you the radial probability curves for the three orbitals I am talking about, that is 1s orbital, 2s orbital and that of the 3s orbital. Now, what you find here is that for 1s orbital, the radial probability, that means if I start from the nucleus, if I move away from the nucleus, how does the probability change? What I find is, for 1s orbital, it happens to be close to 0 at the nucleus. As I move away from this, it becomes larger and larger, comes to a maximum, starts decreasing and comes down to 0 and continues thereafter. For 2s, it is small volume, a small value, starts increasing, comes to smaller maximum, comes back, comes to 0, is very significant here, and starts increasing, comes to a larger maxima, and then that is a kind of trend we have. Similarly, for 3s orbital, I have got the three peaks here, one is small peak, larger one and still larger one. Now, what is pertinent here is, these are the respective positions of these maximas. Now, the significant thing here is, in case of 2s orbital and that of 3s orbital, we find that there is a certain distance here at where we find the probability happens to be 0. This is called as the radial node. That means, as I move from the nucleus and at a certain distance the probability comes to 0, it starts increasing thereafter. So, there is one node in case of 2s orbital, and for 3s orbital there are two such positions here at which the probability becomes 0. So, there are two radial nodes and so on and so forth. In general, what we have is that there are n minus L minus 1 radial nodes in any orbital. So, there is none in 1s orbital, there is 1 in 2s orbital, and there are 2 in the 3s orbital, that you can work out by using this simple formula here. Now, what do we infer from it? What do we infer from it is that, let us see, because we are familiar with s orbital to be spherical, let us understand how is it spherical. Okay. Have a look at it. You have a nucleus here. Okay. I am looking at 1s orbital right now. From the nucleus, the probability is very close to 0. I am trying to move away from the nucleus. Let us see what happens. When I am trying to move away, the probability is increasing, comes to certain maxima, comes down to 0 and continues. That is in this direction. If I go in this direction, again it will increase, come to maxima. If I come in this direction, it will increase, come to maxima, come down again. That means I can move in all possible directions from the nucleus, and in each direction same thing will hold true. That is, in each direction there will be a maxima at a certain distance. If I put all these maximas together, that will happen to be a sphere. That is why we say s orbitals are spherical in shape. If you look at that of the 2s orbital now, it again will be a larger sphere, because in this case the probability is very small, comes to maximum, comes down to 0, increases, comes to larger maxima here. If I do that thing all over in all possible directions, all 360 degrees, I will find that it will be a larger sphere. 3s will be still larger sphere. Now, if I just try to look at the three probability curves in one picture, what I find is that for 1s orbital, so that is a kind of peak position. For 2s, that is a major peak there. For 3s, this is a major peak. So, what we find is that 1s orbital is very small, 2s is larger one, 3s is still larger, because that maximum comes at a much larger distance. But there is something in between there, we will talk more about it as we proceed. Okay. Now, if I look at the angular dependence of atomic orbitals, we find that, if you remember, we just when initially I showed you the wave functions, we find that in s orbital wave function there is no theta or phi term. So, it has only the radial part over here. And if I look at it, as just mentioned, that all of these happen to be spheres. So, what I find is 1s happen to be a small sphere, 2s is a larger sphere, 3s is still larger sphere. Now, but what about that smaller maximas in 2s and 3s? To understand that, let us have a look at that. If I look at this 1s orbital and make some kind of a cut into this, like what we do is you take a large watermelon and then try to slice through and see that the whole core comes in from there. If I do slicing of it here, what I find is, in case of 1s orbital, there is a nucleus in the center there, and then as I move away from this, there is a maximum region here, there is a peak over here. In case of 2s, there will be a tiny nucleus inside, and as I move away from this, they become slightly larger, and then it comes down, then it becomes 0 and becomes a larger one. For 3s, what I find is that there will be a tiny nucleus there. As I move away from the nucleus, the probability increases, come to a smaller maxima, then still larger maxima, and then largest maxima there. Let us look at another picture here. So, that is what I am trying to refer to. So, for 1s, because these are the probability curves I have tried to superimpose on these pictures, on that cutout pictures there. Let us look at a still closer view. Look at this picture of a 3s orbital. In case of 3s orbital, because we are familiar with s orbital to be spherical, fair enough. But what I find is that right here is my nucleus here. That means there is some kind of an internal structure I am trying to refer to. At the nucleus, close to nucleus, probability is close to 0. As I move away from this, the probability becomes, come to a smaller maxima here, it becomes 0, continues, becomes larger maxima, comes to 0, and then continues, becomes still larger maxima. So, what I find is, though we say s orbitals are spherical, what I am finding is 1s orbital, 2s orbital and 3s orbitals have different kind of so called internal structures, or the probability of finding 3s electron close to nucleus is finite, because that is what is meant here. Because when I say this is, I am talking about the 3s electron. 3s electron has a reasonably good probability to be found very close to a nucleus. So, that is what is referred to as the penetration, because we know that s orbitals are more penetrating than the p orbitals, which are more penetrating in the d orbitals, and so on and so forth. So, that is the meaning when we say it is penetrating, because s orbitals can reach very close to the nucleus. Now, let us see what happens in case of p orbitals. In case of p orbitals, what we would do is that if we do the same exercise all over again, that is, I plot the radial distribution curves, wherein I show that how does r vary as a function of small r, or then thereafter I plot that for the probability density, that is r square versus r. I get similar curve as we have in case of my s orbitals. But what is important is, what is important for me to share here is that if I look at the radial probability curves, that is 4 pi r square versus r curves, when I do that, I find that for 2p orbital, we find that there is a maxima and then it comes down, comes to 0. For 3p orbital, I find that this value is very small here, comes to a smaller maxima, comes down to 0, starts increasing, comes to a larger maxima, and continues like this. Essentially, the point I want to bring home is that if I look at the radial probability function, I find that is different for 2p and 3p orbitals. And as before, as in case of s orbital, we find that even for p orbital, that the size is much larger, the 3p is much larger than that of the 2p, that is fine enough. But the second point which is important is that even for 3p orbital, there is something inside, there is a smaller maxima there. That means, if I look at, if I can look at the p orbitals and the spherical part, that is the radial part of it, and try to peep into that, I will find there will be a smaller maxima there. Okay. So, that is what I wanted to bring home. Same exercise we can continue with the 3d orbitals again. So, here again I will find that this is r versus r is r square, this is my probability curve. So, this is my radial distribution curves, this is my probability distribution curve again. So, we find that I can continue doing the similar kind of exercise. We find that radially speaking, all the orbitals happen to be spherical in shape, because if you look at radial distribution curves, I find that each one of them will start with certain smaller value close to nucleus. As I move over from the nucleus, the value increases, come to certain maxima, maybe 1 maxima, 2 maxima, and so on and so forth. But effectively, each one of them has certain kind of maxima coming there. And if I try to look at, visualize them all, starting from the nucleus and going in all possible directions, I find that as regards the radial distribution curves go, or radial wave functions are to be interpreted, they all will give me that the orbital happens to be spherical in shape. Now, let us look at the angular dependence of p orbitals. S orbitals, there is no angular dependence, each one of them happens to be spherical in shape. But when you look at the p orbitals, what I find is, because you remember in the wave function, the dependence was on either on theta or theta and phi, both of them, and so on and so forth. If I look at the things, this is something which I want you to really focus attention on to, because we made a mention earlier, that is the total wave function is made up of 3 parts there, that is r part, theta part, and phi part, and theta phi part are put together is called as the angular part here. Just now I made a point here, that is radially speaking, each orbital has a spherical distribution as per the radial part goes. But say for p naught, that means for p orbital, when L is equal to 1, m is equal to 0, if I plot that, I find that the angular part will have this kind of a representation, but my total wave function will be the product of r part and the angular part. So, if I make a multiplication of these two together, I will try to show it diagrammatically, that is wherever this happens to be 0, this will try to make the spherical part 0. So, the resultant will be something of this kind. So, my p orbitals will be that is especially the pz orbital will be of this shape, because if I try to plot the angular part of pz orbital, which depends only on theta. So, that is the kind of shape I have. So, if I make the product of the two together, I will get the resultant shape to be so called dumbbell shape. So, pz is my p naught is my pz orbital. So, the important point here is the overall orbital shape is the resultant of the product of the radial part and the angular part. Now, what is interesting here is that different pz orbitals are different. Now, this is what I wanted to tell you earlier, that is different p orbitals, though all of them have got overall shape to be dumbbell shape, but because the probability distribution curves were different for 2pz, 3pz and 4pz, we find the distribution curves are different. So, accordingly, they have got different kind of shapes over there. Now, what about the p plus 1 and p minus 1 orb? That means when when my magnetic quantum number happens to be plus 1 or minus 1, then what is the shape of the orbital? 0 is pz, fine. If I look at plus 1 and minus 1, I find that if you look at the wave functions happen to contain some kind of an imaginary or a complex part. Because of the complex part, so I cannot really visualize it. So, what is normally done is, that is, we try to create real functions by combining these two parts, and we make use of Euler's theorem. We have done that earlier also in case of particle in one dimensional box. When I do that, what I generate is, I generate an orbital called as 2px orbital, which is made by combination of 2p plus 1 and 2p minus 1. That is a constructive combination here, and 2py is created by destructive combination of p plus 1 and p minus 1. If I do that, if I combine these two orbitals in two wave functions in this way, I generate what are called as the px and py orbitals. Px and py you cannot really correlate with it. We can't say that px is p plus 1 or py is p minus 1. No, we cannot say that. What we are sure about is that p0 is pz, fine. But as regards px and py, both of them are created from combination of both the orbitals. So, we can at best say that px, probably the magnetic quantum number could be plus 1 or minus 1 or both put together. There is a combination there. So, you have to be clear about it. Now, so that is the kind of shapes which we are familiar with. That means that shapes of, this is my px, this is my pz, this is my py. So, I have just shown it here that ml happens to be plus minus 1. Here also plus minus 1, and this ml happens to be 0. So, p0 is pz, no ambiguity. So, another thing which we have to make a note of here is that when I draw any orbital of this kind, I have shown that there is a positive sign, there is a negative sign there. This plus minus is not charge. This basically refers to the sign of the wave function in that region. That means, if I try to plot say pz, so in this region pz orbital will be the sign of wave function will be positive, in this side it will be negative. So, this positive and negative signs indicate the sign of the wave function and not the charges. What about the d orbitals? If I look at the angular dependence of d orbitals, again story goes parallel to what we have in case of p orbitals. Now, the angular part of the wave function for d naught, that means when ml happens to be 0, depends only on theta. So, the other d orbitals, they depend on both theta and phi. So, thereby what happens is, again similar to what we had in case of p orbital, here again we say that d naught is dz square, because when I say my azimuthal quantum number happens to be 2, magnetic quantum number happens to be 0. Okay. So, for the d0 orbital, what I find is that since it depends only on theta, so it will be symmetrical around the z axis. So, that is the kind of shape I get for the dz square orbital, so to say. On the other hand, similar to p orbitals, what we have is the wave functions for the d plus minus 1 or p plus minus 2 orbitals, they have got imaginary or complex component. So, here again we cannot really have real orbitals out of it. So, what we do is, the real functions again are obtained by taking their linear combinations using Euler's theorem again, and what you find is that d plus minus 1 orbitals, when combined linearly, one is constructively, one is destructively, that gives rise to two d orbitals. They happen to be dxz and dyz orbitals. Similarly, d plus minus 2, that means when ml happens to be plus 2 and minus 2, these two orbitals are combined together to give me dxy and dx2 y2 orbitals. So, we have to be clear, we have to be very clear about it, that d naught is dz square. For other d orbitals, we cannot ascribe a suitable magnetic quantum number to that, because they are the ones which are created by combination of different magnetic quantum numbers wave functions there. Okay. So, these are my familiar shapes of my d orbitals there. We see that dz square has ml to be equal to 0, and then this dxz and dyz are coming from when ml happens to be plus minus 1, and similarly here we got plus minus 2, this is my dxy and this is dx2 y2. So, they are the 5 d orbitals which you are very familiar with. So, I think that is all I wanted to talk about the shapes of orbitals, because we have seen why s orbitals are spherical, p orbitals are dumbbell shape and why they are dumbbell shape, and then of course, we have also seen the shapes of d orbitals, and also we have seen that in case of p orbitals and d orbitals, how do we really account for the magnetic quantum number. So, I will restate here that when we have got ml to be equal to 0 for p orbitals, that is my pz, ml to be equal to 0 for d orbital happens to be dz square. For other orbitals, we cannot specify what is the magnetic quantum number there, because they are the ones which are obtained by combining different orbitals there. Okay. Let us sum up what we have done today. What we have done today is we briefly reviewed the contents of my previous 2 sessions there. Thereafter, we discussed kind of what are the wave functions we have for hydrogen atom or hydrogen like ions there, the nature of the wave functions there. Then we described the radial wave functions and explained their significance, because we have seen that when I try to plot radial distribution functions, whether I plot the radial distribution functions or radial probability functions, so each one of them has its own significance over there. And then thereafter, we explained the significance of angular wave functions in determining the shapes of orbitals, because we know that the p orbitals are dumbbell shape because of the reason that the angular part happens to have the dumbbell shape, because radially speaking all of them are spherical. Similarly, for d orbitals, the shapes are like that, the so called rosette shape is there because the angular part happens to have that shape. And then also in this process, we have been able to explain the shapes of simple orbitals, that is s, p, d and so on and so forth. We did not go on to the f orbitals, same thing can continue over there too. I think with this we are completing our discussion on hydrogen atom. In the next session, we will try to move now to molecules. So far, we started with some kind of model systems, then we came down to atom, that is hydrogen atom. Now, we will like to move to molecules. Thank you.